Single-board controllers, such as an Arduino, are amazingly powerful and inexpensive maker hardware, with the potential to support industrial applications. However, by industrial standards, they are fragile and difficult to integrate with common hardware used in typical panel building. Nonetheless, they are easy to program, and many control engineers find them a versatile solution for small-scale projects. To solve this conundrum, Automation Direct has developed an industrialized controller built with housings and form factors typical of conventional PLCs. The Productivity Open Arduino Maker Zero compatible controller is DIN rail mountable and works with other Automation Direct communication and I/O modules to support connectivity common to industrial control panels. This demonstration project set out to create an industrial-type application using the Productivity Open and associated components to see what advantages they offer over conventional maker hardware. Previous microcontroller projects included using an Arduino to control a flow loop and a Raspberry Pi to perform model-based control. The project objective involved controlling a hot air heat gun to solder large components. The gun produces about 1,500 watts of output, and it directs heat toward a copper heat spreader positioned on a special table to facilitate mounting a transistor. The challenge is controlling the heat output at a specific, steady temperature using a PID loop. An Arduino-based controller can easily handle the data processing when provided with an accurate temperature measurement of the copper plate using a thermocouple. Automation Direct's Productivity Open P1AM 100 CPU works with the Arduino Integrated Development Environment and interfaces with the Productivity 1000 series communication and I/O modules, as well as maker-oriented interface shields, so hardware can be combined as needed. Adding a standard temperature input module provides the interface and data processing for a Type J thermocouple. The sensor attaches directly to the copper plate to provide robust and responsive temperature data. The Productivity Open prototyping shield is used to support additional bits of circuitry, and adding a bracket and two DB9 connectors simplified the necessary connections. The heat gun is controlled using a zero-voltage switching solid-state relay driven by a digital output pin from the CPU to turn the gun on and off to throttle its output. The AC power line phase is sensed by an input pin to the CPU to synchronize with the solid-state relay. To provide a mechanism for data display and control, a Maker Community Adafruit 772 16x2 LCD display device with push buttons communicates to the CPU via an I2C interface, using only two digital pins to drive the display and scan the push buttons. With all the control interfaces working, the next step was creating application code, including the PID algorithm. The operator starts and stops the control algorithm as required. The simple state machine allows cycling through each of the settings via the left and right buttons, while adjusting parameters with the up and down buttons. The select button is used to start and stop the PID control. Two lines of 16 characters display all the necessary information, including the actual temperature in the top left, with the set point immediately below. The throttle setting is shown in the bottom center, along with the current state of the state machine. As with any loop application, PID tuning was necessary to overcome temperature overshoot and oscillation. So what does this project tell us about the controller? Why use it? A conventional Arduino has many capabilities. It is inexpensive, and it is easy to program using C or C++. To many engineers, this is a very clear choice, but not without its drawbacks. First, the physical fragility. Second, various interfaces such as reading a temperature sensor or other type of industrial instrument must often be built from scratch. A small PLC can also handle the necessary control requirements, and it will have accessories designed to act as interfaces to those external devices. It will also be more physically robust and easier to assemble using standardized DIN connections and DIN rail mounts. A PLC features specialized software with background utilities that identify when problems are developing and can warn the operator or shut down to a safe state. These capabilities are not part of the native Arduino IDE. The main downside of a PLC is its higher cost, combined with its ladder logic programming environment which is foreign to a typical maker. An industrialized Arduino, such as the Automation Direct Productivity Open, is a useful compromise between those two extremes. Industrial form factors overcome the fragility of unprotected boards and simplify connectivity. Modular interfaces for industrial sensors and peripherals are available. Hardware versatility allows use of industrial and maker devices, including DIY adaptations. Programming using C and C++ is possible, along with other platforms, including productivity blocks. However, the lack of protective and housekeeping software functions available from a PLC should give an engineer pause to ask, what could potentially happen with this system if the controller fails? An engineer considering a small-scale project such as the one here has some critical questions to ask, but it is always helpful to have the widest variety of options available.